Okay, now we have this understanding that the temperature is directly proportional to the average kinetic energy of the particles in a given piece of matter, whether a solid, liquid, or gas. And let's just take a minute to talk about this idea. So we used a gas as our example with a number of atoms moving around in a given volume, and this time I'll draw the container. Okay. Well, just as these atoms are all moving with a particular kinetic energy in given directions, the same thing applies to a liquid. Sorry, I don't know exactly why things are going crazy on the screen. Hold on one second. Something's happening, and I'm not sure what. Okay, fix that problem. Just as in a gas you have these atoms all moving around in a given direction, in a solid, we'll talk about liquids in a little bit, but in a solid, so here's a solid, and you have these atoms are all packed in closely right next to each other in a lattice. This is a crystal, where you have this orderly structure of atoms packed in next to one another. Well, it turns out that each of these atoms is also jiggling back and forth, up and down, all around. Each one is jiggling, but it's not changing its position in this lattice or network of atoms. It's just shaking. They're all shaking about, kind of jiggling about and shaking back and forth. And that shaking has a velocity, and you can do the exact same thing, and you can draw your histogram of your number of atoms. Sorry about the non-neatness of the writing. And this is the energy. You can do the exact same thing we did before, and you get the same bell curve. And again, this is your temperature, the temperature of your solid. Okay? Now, you may have heard the term absolute zero. Absolute zero. And this is the coldest theoretical temperature possible, and which would be 0 degrees Kelvin. It's on the Kelvin scale, which would equal negative 275.15 degrees Celsius. Okay, that's absolute zero. And in a substance that was at absolute zero, the atoms would have no kinetic energy. Well, this is not possible because of our good and mysterious friend quantum mechanics. There will always be some vibration within your network of atoms, and so absolute zero is not attainable. Here's something to consider. How would you measure absolute zero? You would have to either stick a thermometer in there, when your thermometer would have temperature, so the thermometer would upset the system and it would no longer be at absolute zero. Or let's say you could measure it by bouncing light off of it somehow. Well, the second you hit your substance with a photon, here comes Mr. Photon, it's going to cause the atoms to vibrate, upsetting your absolute zero. So you can't measure it. And also there's other reasons that it's not really attainable. Now you can look up in your book or online, you can look up how to convert from Kelvin to Celsius. It should be pretty clear from even what I wrote here that the Kelvin scale is just offset by just over 275 degrees. So, but proportionally, Celsius and Kelvin are the same. So 1 degree Kelvin changes just as much as 1 degree Celsius, but it's different than Fahrenheit. But you can look up all those conversions. But it's all measuring the same thing, which is the average kinetic energy of your substance. Getting things really cold it's very useful in physics. You know, interesting things happen when stuff gets really cold. You enter into strange quantum states of matter, such as superfluid helium, which is a superfluid substance, has no friction, and it will slide up the walls of a glass container and empty itself out, doing all kinds of strange things. Superconductivity, metals, certain metals will become superconductors when they get very cold, and that means they have no resistance. We'll learn about that later when we do our lessons on electricity. So it's a really interesting thing to get things really cold. It's also technically very challenging to get things very cold. Now, anyway, that aside, I want to talk about some basic things which you probably know about temperature. Let me get this to happen here. Let's get a new page. Here's some things you probably know about. You've probably heard that heat flows from hot to cold. Okay? Well, there's really no mystery here. It's explained very simply from our understanding of the fact that everything's made of atoms, and all those atoms are always shaking and bouncing into each other. So let's do an example. You have a cup of cold water, and you have another cup of hot water. Now you stick a thermometer into each cup of water, and so let's say this one is, we'll use Fahrenheit because it's something we're more familiar with, right? 35 degrees Fahrenheit. Sorry, it's not writing where I want it to. And say this one is 200 degrees Fahrenheit. So big temperature difference. Then you put in a piece of something that's a thermal conductor. If you say a bar of metal, right? So you stick this piece of metal between the two cups, and what's going to happen? We know from our experience that the metal's going to start to heat up, and it's going to heat up the cold water, and this temperature here is going to start to increase, and this temperature here is going to start to decrease, and eventually they're going to become the same temperature. But why does that happen? It should be clear that you've got all these hot atoms bouncing around with really big kinetic energy, and they're banging into the metal, and then they start bouncing the metal, shaking the metal atoms around, and literally those vibrations, here's my vibrations, start to propagate and travel through the metal. So all of the kinetic energy of the atoms in the metal starts to go up, and then the shaking metal starts to shake into the molecules of water on this side, and lo and behold, after a certain amount of time, the heat transfers. So it should make sense why heat flows from hot to cold. This comes directly from just an intuition of, if you know that heat is atoms shaking and banging into each other, they're going to bang into other atoms and cause them to heat up and transfer some of their energy to the quote-unquote colder atoms. They're just going to transfer some of that kinetic energy. And so that's why heat flows from hot to cold. And this is a great experiment to do with kids to start teaching them something about how temperature works. Okay, next we will be talking about the states of matter.